of oxide particle.
Uh, Predominantly, we will be talking about the same aspect of the iron oxide
Oxide
nanoparticle,
nanoparticle,
which
which
we
we
have
have
learned
learned
for
for
the
the
gold
gold
nanoparticle
nanoparticle
and
and
the
the
synthesis.
synthesis.
Some points which are very unique in this case. So the focus is on that very important point, that is the surface activity. You have seen that we have
Have
defined
defined
or explained the
the
definition
definition
of
of
surface active molecules.
cues
Those prefer to remain active at the
that the
interface,
is
no
no
matter which interface
if
it
it
is.
is.
So
So
now you will see
see
that
that
how
how
can
can
we produce synthesized
size
surface
surface
active
active
nanoparticles. So there's a difference between, I'll explain in this lecture, that
that
what
what
is
is
the
the
difference
difference
between
between
surface
surface
active
active
molecule.
molecule.
You are
You are
very
very
familiar
familiar
about
about sodium todicyl sulfate, which you added in the gold nanoparticle suspension yesterday to make it a stabilized colloidal suspension. So, sodium dodicyl sulfate is a surface active molecule, and in I'll explain that how we can produce the surface active nanoparticle. So, if somebody asks you that dimensionally, how big is the nanoparticle in comparison to a molecule?
So the molecule,
Molecule,
the
the
dimensions
dimension
of the
of the
molecule
molecule
lie
lie
within
within
1
1
to
to
2
2
nanometer
nanometer
range.
range.
It's
It's
very
very
tiny
tiny
size.
size.
Smaller
Smaller
nanopartic molecules
molecules
are
are
like
like
carbon
carbon
dioxide.
dioxide.
They are
They are
even
even
less
less
than
than
1
1
nanometer in
nanometer in
size,
size,
most
most
of
of
the
the
molecules.
molecules.
But the
But the
bigger
big
molecules like surfactant
surfactant
with
with
long
long
hydrocarbon
hydrocarbon
tail.
tail.
So you
So
may
you may
say
say
that
that
their
their dimensions
dimensions are close to 1
are 1
to
to
2
2
nanometer.
nanometer.
So
So
usually
usually
close to
close to
1
1
nanometer.
nanometer.
But the
But the
nanoparticles,
nanoparticles,
the
the
surface
surface
active iron
iron
oxide
oxide
nanoparticle, which
nanoparticle,
we
which
will
we will
talk
talk
about.
about,
So
so
their
their
size
size
is
is
close to
close to
25 to
25 to
50
50
nanometer.
nanometer.
Means
Means
at
at
least
least
25 or 30
30
times
times
bigger than the
than the
surface
surface
active
active
molecules.
molecules.
So the
So the
obvious
obvious
question
question
is
is
that
that
if we
we
have
have
the surface
surface
active
active
molecules,
molecules,
we
we
know
know
the
the
properties of
properties of
surface
surface
active
active
molecules
molecules
from
from
the
the
molecular
molecular
structure
structure
of
of
the
the
molecule.
molecule.
The
The
molecule is
molecule is
possessing the
possessing the
polar
polar
head
head
group
group
and the
and the
non-polar
non-polar
hydrocarbon
hydrocarbon
tail.
tail.
How
How
can we
can we
define
define
those
those
aspects
aspects
in the
in the
surface
surface
active
active
nanoparticle?
nanoparticle?
So
So
this
this
this we
this
are
we
going to see
see
in the
in.
next chapter. Okay,
Okay,
so
so
again,
again,
some of
some
the
of the
very
very
fundamental
fundamental
basic
basic
concepts.
concepts.
We
We
have a
have a
beaker
beaker
full of
full of
water,
water,
and we
and
identify the interfaces and
interfaces and
aqueous
aqueous
bulk.
bulb.
This is
This is
the
the
water interface, exactly
exactly
the
the
surface of
surface
the
of
water,
water,
and
and
this is
this
the
is
solid liquid interface. So because of the container and the interior of this liquid interface we call aqueous bulk. What if we add ammonium chloride salt, a very small
small
amount,
amount of,
you may
you may
say
say
1
1
millimolar,
millimolar,
10
10
millimolar,
millimolar,
and as soon as we are going to add
add
this
this
ammonium
ammonium
chloride,
chloride.
it's an
It's an
electrolyte
electrolyte is
split
split
into
into
oppositely
oppositely
charged
charged
ions.
ions.
So ammonium ion tetrahedral shape and the chloride ion. For the time being, you just ignore chloride ions because they
They
are
are
the
the
spectator ions, and the ammonium
ammonium
ion
ion
is
is
solubilized
solubilized
by
by
the
the
hydration
hydration
layer
layer.
because
Because
of
of
the
the
ion
ion
dipole
dipole
interaction. Ammonium ion is an ion. The dipole of the water, element of the water dipole, will be directed towards the cation, and hence you have the ion dipole interaction, and you have a hydration sphere. Those water molecules which travel under
Under
the
the
dynamic
dynamic
motion
motion,
during
during
the displacement of
displacement
the
of the
cation
cation
in
in
the
the
aqueous
aqueous
bulk,
bulk,
they
they
will always
always
remain
remain
bound
bound
to
to
the
the
water
water
molecule,
molecule,
and
and
hence
hence
they
they
are
are
included
included
in the
in the
hydration
hydration
sphere.
sphere.
They are
They are
not
not
going to
going
be,
to be,
they
they
may
may
be
be
exchanged
exchanged
among the
among the
water
water
molecule
molecule of the
bulk,
bulk,
but the
but the
total
total
number of
number of
water
water
molecules,
molecules,
those
those
are
are
present
present
in the
in the
hydration
hydration
sphere,
sphere,
they are
they are
not
not
going to
going to
change.
change.
What if we
We
replace one
one
hydrogen
hydrogen,
out of the four
four
tetrahedral
tetrahedral
positions
positions
with
with
the
the
hydrocarbon
hydrocarbon
functional
functional
hydrocarbon
hydrocarbon chain
chains of
of
C8,
C8,
C10,
C10,
C12,
C12,
C14,
C14,
any
any
number
number
of
of
the
the hydrocarbon chain methylene group.
Okay. Now
Now
there is
there's
a
a
problem.
problem.
When
When
you
you
add
add
a
a
non-polar functional group, then the non-polar functional group that is in repulsive interaction with that of the water
water
molecule
molecule
because
because
they
they
are
are
polar.
polar.
But the
But the
polar
polar
functional group can easily interact with the water molecule. Now there is a competition between the polar-polar interactions and the polar-non-polar interaction. Those interactions which will predominate the other, they will decide the fate of the molecule. If the polar-polar interactions are greater in magnitude, in comparison to the non-polar interaction, the molecule will stay in the aqueous bulk. If the non-polar-polar interactions are going to predominate, in comparison to polar-polar interactions, the molecule will be expelled from the aqueous bulk. So, this property of the dual affinity or the dual functional group with opposite with polar and non-polar polarities provides the amphiphilicity or the amphiphilic property to the molecule. So molecules, such kind of molecules are known as amphiphilic molecules. Amphiphilic molecules like over here polar and non-polar. Now quantitatively or the suppose if you want to just estimate under what circumstances the amphiphilic molecule is going to remain in the bulk or
or
excluded
excluded
from
from
the
the
bulk
bulk
or
or
prefer
prefer
to
to
remain
remain
at
at
the
the
interface
interface
is given by
hyd-
hydrophilic lipophilic balance HLB scale.
scale.
You can calculate it theoretically. So there are different methods to calculate that. It's a very common scale. You can see it on the internet. You can easily perform the calculation. You can choose STS and try to see what is the value of HLB for sodium chloride sulfate. The scale runs from 0 to all the way 18. Now, when the HLB value is somewhere over here, higher than 9, close to 9, up to 18, the molecules with HLB number resides within this part of the scale. They are highly hydrophilic, highly water soluble. It means that if they are highly water soluble, it means that the polar-polar interactions are predominant in comparison to non-polar interaction. The molecule will reside in the aqueous bulk. On the contrary, if the HLB number for the molecule resides lower to that, less than 6, somewhere between 0 to 6, the molecule is much more predominantly non-polar. It means the polar-non-polar interactions are going to predominate, and hence the molecule is going to be expelled, and that's why it is predominantly hydrophobic molecule. Now, what if
If
we
we
have
have
a
a
delicate
delicate
balance
balance
between the
between the
polar-polar and non-polar interaction, then
then
the
the
HLB
HLB
number is
is
somewhere
somewhere
over
over
here,
here.
7, 8, 9. When the HLB number of a molecule is close to 7, 8, 9, then the molecule is going to absorb at the interface. Air, water. It prefers to absorb at the interface. So HLB scale is a kind of a scale which helps us to determine
Before performing any kind of experiment that whether a molecule would be predominantly
non-polar
polar
or
or
predominantly
predominantly
polar
polar
molecule
and
what kind
kind
of
of
surface
surface
activity
activity
we
we
are
are
expecting.
expecting.
This is
This
the
is the
fundamental
fundamental
information
information
regarding
regarding
the
the
amphiphilic
amphiphilic
property
property
of a molecule. We will
we're
be using
using
this.
this.
So I
So I
have
have
explained
explained
this
this
definition
definition
because
because
we
we
will
will
use
use
this
this
when
when
we
we
talk
talk
about
about
the
the
surface
surface
activity of
activity
the
of the
magnetic
magnetic
nanoparticle.
nanoparticle.
Now, when we add this
This
kind
kind
of a molecule,
of which is surface,
which
which
has
has
a HLB
HLB
number within
within
this range, it prefers to absorb at the interface, and
and
we
we
keep
keep
on
on
increasing the
increasing the
concentration,
concentration
some
some
point it starts
start
forming the
twice,
mice, which
which
I
I
already talked about in the previous lectures. And you can determine the critical muscle formation by by performing the surface active experiment or the connectivity experiment if the surface active molecule is high.
Now, these were some of the preliminary or basic fundamental considerations. What if we take a gold nanoparticle,
We have few
two gold nanoparticles, we drop it in the glass of water.
and we try to understand that what happens then. As I told you that a bare gold nanoparticle, if you simply drop it in the aqueous phase or a glass full of water or a beaker full of water, right? And then now what kind of interactions we are expecting? So gold is a transition metal. There is a free electron cloud on the surface. Does the free electron cloud provide sufficient potential to interact with the dipole of the water? I mean to say,
This cloud you could see is the free electron cloud, mobile electron cloud, and these angled, they are the water molecule, band structure of the water molecule. Is it possible to have the interactions
electrostatic interactions
with, among
the free electrons, mobile electrons, and the water molecule? This is not happening. The reason is because if this is happening, then you do not need to add the surfactant to provide the colloidal stability. Then the nanoparticles, they themselves are the colloidal particle and they can produce the stable nanoparticle suspension, but they are not. What will happen if you are simply adding the gold nanoparticle, then van der Waal interaction, matter attracts matter, van der Waal interaction predominate than such kind of interaction. You cannot exclude these interactions, but they are not strong enough to provide the colloidal stability. So then the van der Waal interactions predominate, thereby the nanoparticle which you have added in the aqueous bulk, they will fuse one another and they will settle at the bottom under the effect of gravity. So this is the case
happens without the stabilization. And
in order to avoid that, we add the surfactant molecule. Yesterday we added the STS to make a clear suspension, a better suspension. Right? So that is the purpose. When you add the STS, that is a surface active molecule, it will provide the colloidal stability, and hence now those nanoparticles which were tend to fuse with one another in the absence of surface active molecules, now they are stabilized by the presence of the surface active molecules. Now the van der Waal interactions are no more predominant than that of the electrostatic interaction, because there is a bilayer created around each nanoparticle by the surfactant molecules. You see over here. So, if we add sodium chloride will not help to provide the colloidal stability, but we have to add amphiphilic molecule. Sodium chloride is not an amphiphilic molecule. It is simply made up of two ions, oppositely charged ions, sodium and the chloride ions. So therefore they have no any ability to provide the colloidal stability. But on the contrary, if we have the amphiphilic molecule with the long hydrocarbon functional group, that is the hydrocarbon chain, so that will provide a bilayer. You see the bilayer now? This bilayer is traced with the head group of the cation or the anion. Whatsoever is the ionic surfactant is there, that is the charge on the surface. Now this charge will not allow another similar gold nanoparticle coated with the bilayer to fuse with this, because the charge, similar charge, the same charge, the same kind of a structure you would expect on another gold nanoparticle. When these gold nanoparticles, they come close to each other, the similar charges or positive charges are going to repel, and hence they are not going to fuse one another. These are known as electrostatic repulsion. You see, this is bilayer on one gold nanoparticle. This is bilayer another gold nanoparticle. This is positively charged if the surfactant or surface molecule is positively charged. Here also positive charge, so therefore repulsions are going to occur, and hence there is no way this gold nanoparticle fused with this and hence you achieve the colloidal stability. This is what I explained from the DLVO theory at that time, right? So VR and VA. VR is the electrostatic potential, VA is the non-electrostatic potential. In fact, the two interacting gold nanoparticle. So it all depends on the predominance of one potential over the other, and whatsoever is going to win, they are going to decide the fate of the particle. So when you use the surfactant VR predominates over the VA, and hence the repulsive interaction set in, the potential energy instantaneously increases. This is the potential energy curve for the electrostatic repulsions. This is the potential energy curve for the non-polar van-der-Waals interactions, attractive interaction, and in this case potential energy falls and lead to flocculation. You know the word flocculation or coagulation? So they are the irreversible process. When the coagulation among the gold nanoparticle or the nanoparticle particles happen, you cannot reverse it. It is an irreversible process. So this is what the solution you made yesterday by adding SDS.
And now each nanoparticle having the bilayer of the surfactant, and as you see, you have the bright blue reactor,
and that provides you the absorbance sharply close to 520 nanometer. So this was the story for the gold nanometer. Now, what if I'm going to synthesize nanoparticle in the hydrothermal container? So I'm going to explain what is the meaning of that. The reaction which you perform this one, gold ions by treating them with sodium citrate or sodium borohydrate, the reaction which you performed in the lab yesterday. So that was a straightforward reaction occurring at the room temperature. And we have another reaction. If you take iron sulfate, ferrous sulfate, ferric chloride, if you mix the solution of these two,
and then you add ammonium hydroxide, that is the base, you can initiate the reaction to convert them into iron oxide, FeCO4.
This reaction can also be performed at the room temperature. You don't need any kind of special experimental condition. But this will not produce the crystalline, well-defined iron oxide nanoparticle unless after completing the reaction you are going to place it in the steel container including the Teflon container placed in a steel jacket. So here is the Teflon container. Teflon is non-reactive, and here you have the steel jacket, and there is a steel cover. You can tight it. You perform the reaction at the room temperature. You pour the contents into the Teflon container, tight it. Now you place this at 150 degrees centigrade for 24 hours. Placing it at 150 degrees centigrade for 24 hours, it is not the purpose to complete the reaction. The reaction is already completed. But to perform the crystallization of the iron oxide nanoparticle. So when you perform, apart from this, three components, iron in oxidation 2, iron in oxidation 3, and the base. The fourth component is always surfactant, that is not shown over here.
Because that is not participating in the reaction, it only provides the colloidal stability. So that surfactant is here in the form of a bilayer. Now, though I have shown the same color of the nanoparticle,
you could assume
that is not the gold nanoparticle, they are the iron oxide nanoparticle.
The iron oxide nanoparticle produced over here, I have shown over here. Now, what happens after this? When I place it in the oven at 150 degrees centigrade for 24 hours, the iron oxide nanoparticle, which were not of same shape and structure or the size, when the reaction is performed at the room temperature, but when you are going to perform in the reaction vessel at elevated temperature and obviously elevated pressure, when inside the Teflon container will be much higher than the pressure outside. So we have here it is 1 atmosphere pressure. So what the pressure is going to do, or the elevated temperature is going to do, to alter the physical properties of the nanoparticle. That is the purpose of our understanding in this lecture. This kind of treatment is known as hydrothermal. Hydrothermal means that we have the reaction that has taken place when the water formed in the aqueous phase, thermal at elevated temperature, so under high temperature and pressure condition. So this kind of treatment cannot be performed in glassware containers, because you are going to increase the pressure to a very high degree. So therefore, the reaction cannot be performed in glass containers, so it has to be a steel. The picture of the steel container is here. It is shown like this. It's something like this, quite a big container like this. This rod is to open the lid. The lid of the container is this much thick, and you have to put pressure in order to open it. And inside it is a very heavy steel jacket. Inside it is a Teflon container where you add the reaction products. So instead of using the STS in this reaction or any kind of conventional surfactant, if you use, remember I told you that what is the Gemini surfactant in the beginning of the lecture? If you use this kind of surfactant, the double tape and the double head group, ammonium head group with the bromide counterion, ammonium head group and the bromide counterion. When you use a Gemini surfactant, schematically you can show it like this. A very strange thing happens. The nanoparticles which were suspended in the aqueous bond, if we use a conventional surfactant, but carefully choosing a Gemini surfactant, the nanoparticles are adsorbed at the interface. This is a solid-liquid interface. This is an air-water interface. You see, there is no nanoparticles suspended in the aqueous bond. All nanoparticles are continuous. What is the meaning of this? If you take them out after the annealing, when the crystallization is completed, after 24 hours, Teflon container you can take out, you place the magnet, all nanoparticles are attracted towards the magnet, right? So, here, this is the magnet, this is the nanoparticle suspension. It is water soluble, not surface active. When you place the magnet, see all nanoparticles are attracted towards the magnet. So this will happen. Now when you have this kind of situation, right, and you can simply remove all nanoparticle from the container by applying the magnet, removing the aqueous phase that contains excess of Gemini surfactant. You can purify it with fresh water, and when you are going to suspend it in the aqueous bond, they are going to arrange at the interface. They will never go into the aqueous phase. They will not go into the aqueous phase. Such kind of particles are known as surface active particles. Now, what is the difference in the actual sample of the surface active and the bulk soluble iron oxide nanoparticle? This is the bulk water soluble iron oxide nanoparticle. When you do not use the Gemini surfactant, when you use only the conventional surfactant, this is the water soluble, and the color of the sample is close to brown color, yellow brown color, because of iron oxide. It's a rust color. Rust color is the same thing. Right. The surface active, they are not suspended, they are only, you see the black band? The black band consists of very tiny particles which are only arranged at the interface. If you pick them to prove that they are indeed surface active, you can suspend it into a solution of biphasic solution of organic and aqueous. You can choose any organic solvent which is not miscible with water. So there are plenty of organic solvents which are not soluble in water. Benzene is one of them, right? And when you, for hexane, when you place the surface active iron oxide in such a basic biphasic solution, you will see they are not going to either absorb over here or in the aqueous bulk or in the non-aqueous bulk. They are exactly at the interface. You see the black line, the black band, that is where all the iron oxide nanoparticle exist. Any question up to here? If you have any confusion, you can go ahead and ask me.
Okay.
Now, somebody
Somebody
can ask you, yes, I can see this band of small particles,
But can't I see the real picture of the particle? Yes, you can see. Here is the real picture.
They are
The iron oxide carrying Fe3O4 nanoparticle.
You see over here,
Right?
It
It
is
is
50
50 nanometer scale bar,
It's
20 nanometer scale bar, because from lower resolution we are moving higher resolution and even much higher resolution,
5 nanometer scale bar. You see only 3 particles. They are the iron oxide. You could see the crystal planes. You see the
exactly the way we have the fingerprinting,
the lines of the skin, the cells.
Exactly,
You have the atomic lines over here, and they are the crystal plane. Those crystal planes.
I remember I told
you there are
three different predominant kinds of crystal plane in 111,
100, 110 crystal plane. Right. So these are the lines of the atom, because it's point, sorry, 5 nanometer. So this is the half of this is 2.5 nanometer, then the half of that is maybe 1.7 nanometer, just close to 1 nanometer. So in this way we could see that's a very high resolution image. And the white arrows indicate the coating of the Gemini surfactant that provides the colloidal stability. So there is a very, you see there is a thin layer of the coating that is provided by the Gemini surfactant. And this is the X-ray crystallography to demonstrate the crystal structure. We don't need to go ahead in this, but I'll explain that what kind of crystal structure you could expect. So these are the surface active iron oxide nanoparticles. Now what they do very remarkable things. So microscopically, this layer, how this layer provides the surface active. Actually, the thing is now we want to know that how these iron oxide nanoparticles, they become surface active. How the property of surface activity is induced or introduced by which kind of chemical functionality these nanoparticles are possessing. So I am simply taking up, it's a part of the surface of the nanoparticle, and this is the way the Gemini surfactants are arranged. Each surfactant, so a molecule possessing 2 hydrocarbon tails, and the hydrocarbon tails are entangling with the adjoining hydrocarbon tails from the other molecules. It is forming a bilayer. Eventually I have shown a monolayer, but bilayer, and then provides a colloidal stability. What happens when we place this structure at elevated temperature and pressure? I am talking about this one. When I place this at an elevated temperature and pressure, how I can achieve the surface activity? So when I increase or when I perform the hydrothermal treatment, these hydrocarbon chains become much more hydrophobic. How? Because this is the polar head group. There is some degree of water molecule
close to the polar head group. But when hydrothermal treatment is provided,
all
the water molecules are expelled.
and the environment over here becomes very intense non-polar environment. What if I have the longer spacer? This is the spacer. We call this as a spacer, which connects the two identical parts of the molecule. If we have another Gemini surfactant with a longer spacer, so that folds between the hydrocarbon tails. Bottom line, you could have a different kind of Gemini surfactant, but not all Gemini surfactant provides the surface activity or produce surface active nanoparticle. The problem, where is the problem? The problem is that if you introduce a longer spacer, that reduces the compatibility of the hydrocarbon tail and reduces the steric hindrances. If you have a bigger head group, so that also increases the distance among the hydrocarbon tails and reduces the non-polar interaction. So therefore all those factors which reduces the hydrophobic interactions between the non-polar tails, they are contrary to the surface active effect. So remember I told you the HLB scale that runs from 0 to 80. When you have appropriate Gemini surfactant that could impart the HLB scale close to the number 7 to 8, then the particle becomes surface active. The way I told you over here that a surfactant, a surface active molecule, when the polar and the non-polar functional groups, I mean the compatibility that provides the amphiphilicity somewhere up close to HLB number this becomes surface active, not this, exactly the same way. So the nanoparticle that is coated with the Gemini surfactant, if you choose appropriate Gemini surfactant, and that provides the surface activity or the surface activity HLB number value close to this, then the nanoparticle becomes surface active. Neither this particle with the higher HLB number or the lower HLB number is going to be surface active. So it is not the surface activity of the particle. In fact, it is the surface activity provided by the Gemini surfactant molecule, surface active molecule. But they are absorbed on the nanoparticle. So therefore the total surface active, the total entirety, individual entirety with the layer of the surface active molecule becomes a surface active entirety, and whose HLB number, if resides somewhere over here, the whole entirety becomes surface active. You got more points? This is the story behind that. And here is another very high resolution image showing you the adsorbed Gemini surfactant on the nanoparticle. If the scale is 10 nanometer over here and the particle is close to 50 nanometer, you see the lines. These are the lines of the atoms arranged on a crystal lattice, right? So we can identify that from the spacing and to find out that which crystal plane this is. Now we are going to put them in practice. What they can do. First, macroscopically, we know that the surfactant, the polar head group is in the aqueous phase, aqueous and air. The tails are in the air, right? We know that. But how can we show the surface activity exactly the way we show here for the surfactant molecule for the surface active nanoparticle? Now, it is slightly complicated to understand how the surface active nanoparticle is arranged exactly at the air-aqueous interface. Air is a non-polar, So therefore, non-polar part, non-polar environment can only accommodate the hydrocarbon tails, not the polar hedron. So therefore, the molecules which are adsorbed on the surface of the particle, they should have only tails directed towards the atmosphere. But these tails cannot be directed towards the, air phase, but these tails cannot be directed towards the atmosphere because they are non-polar. So therefore, there is another layer of the particle. This is bilayer, this is monolayer. So this unique kind of molecular arrangement of the Gemini surface active molecules will make the whole entirety of surface active. So you see that they are arranged at the interface or over here. In this while, the particles over here, here and here. What is this? What we did actually, to show the application of the surface active nanoparticles, iron oxide nanoparticle, we took different concentration of the gold nanoparticles as pollutants. You may assume that in a glass of water there are suspended pollutants of particles. You cannot see them because they are in nanometer range. So you could see that the water is clear, so therefore it's clean, but in fact it is not. We took the model gold nanoparticle because a very low concentration of a gold nanoparticle generates a color. We increase the concentration of gold nanoparticle in this solution on this way. So this is the dilute concentration, higher, and maximum concentration. We took the 4 concentration of the gold nanoparticle suspension. We added the constant amount of the surface active nanoparticles above it, and we waited for a few hours. After a few hours, we saw the first 2 solutions are completely clear. Their color reduces, but the color remains. It means that all gold nanoparticles in the first 2 solutions, in the first 2 concentrations, they are taken up by the surface active molecules, surface active iron oxide nanoparticle. But here, the iron oxide nanoparticle concentration is not sufficient. So hence, the excess amount of gold nanoparticle as metallic pollutants, so that remains in the solution. How do we know that the gold nanoparticle as pollutant, they have really taken up by the iron oxide nanoparticles? What we did, we picked this sample expecting that it is the combination of iron oxide and gold nanoparticle sample. We extracted from the solution. It all happens like this. Gold nanoparticles were attracted to that of the iron oxide nanoparticle. Complexation occurred. We placed the magnet, removed the entire sample. Removed the entire sample and looked through the electron microscope. See over here. You have low contrast particle, you have very high contrast particle. It means that at least the low contrast particle, they have the different chemical composition into high contrast particle. When we perform the mapping, we call it mapping. So here we call it is EDS, it is energy dispersive spectroscopy. If you look at it, is basically the photoelectric effect, and it's a first year chemistry. So this facility is included in that instrumentation, and it can only look for, if you tell that we want to see only the gold nanoparticle, so then you will see only the gold nanoparticle. So the emission which is coming out, electron diffraction, electron emission that is happening from the valence electron cloud. So that is the binding energy or the energy consumed, that is proportional to that of the gold valence shell. So therefore here in this image, you see only the gold nanoparticle. So it means that this bright group of the particle is because of the gold nanoparticle. And why it is more brighter? Because the transition metal diffraction is much more intense in comparison to oxide metal nanoparticle electron diffraction. And when you perform the iron mapping, as you could see the all other particles, so there is one iron component, and likewise you can have the oxygen component or any other component as well. So we took one sample from here, and this confirms the presence of gold nanoparticle which were extracted from here. We took another sample and performed the same way, and here we prove that there is also gold nanoparticle. A greater amount of the gold nanoparticle because the higher concentration you see over here, and the iron oxide. So this is the EDS spectrum which explains which elements are present in the sample. So you can simply see it over here. What is the meaning of this whole story? The meaning of this whole story is, instead of using the filtration process to clean the contaminated water, you can use this is much more easier technique. Right? You don't need any filtration process. Simply place the magnetic surface active magnetic nanoparticle sample on the surface of the contaminated water, and your all metallic pollutants, they are going to be attracted towards the sample, and this way you can purify the contaminated water. Where you could expect such kind of contaminated water, all mining industry, iron ore industry, steel industry, so they have the industrial effluents, they possess a very high degree of concentration of suspended metallic particles. Okay, so there is another case over here. It is not simply the blank gold nanoparticle. In order to allow them to be attracted or pulled by the iron oxide nanoparticle, so you have to have the opposite electrostatic interaction. It means that the surface active nanoparticle, if the head group is positively charged, you will be using the stabilizer, colloidal stabilizer, with predominantly negative charge. So these are not the magnetic field because of which the transition metal is going to be attracted with the iron oxide. That's not the case. These are the electrostatic interaction. Then what is the advantage of this? The advantage of this, you are not performing the filtration in anywhere in this case. Simply putting the magnet over here will allow to remove all the pollutants. In conventional purification, so you use the filtration, a very complicated process, but in this case, this is a modern technology. So you will see now, in future, you will have modern technology which can be used for the purification of water without the filtration, and they are much more efficient. So, at the end, surface active magnetic nanoparticles, a new class of nanomaterials with interfacial application. I have shown you just one application, but there are many other applications. I show you other biological application in the next lecture. Since I wanted to first give you the example of the conventional application, which is more easier to understand, right? And it is much more straightforward. Why we need the surface active magnetic nanoparticle for the purification of water, right? But after that, you will see that we are going to apply, we are going to use the surface active magnetic nanoparticle for biological applications. They remove pollutants without incorporating in the atmosphere. You see, they are removing the pollutant, but they are not incorporated in the atmosphere. They remain at the interface. That is the beauty of surface active iron oxide nanoparticle. Otherwise, there are other chemical methods where you are putting the chemical. Chlorination is one of the process where you have to kill the harmful bacteria in the water. So, and you have to flush the chlorine through the water, and then when you fill the glass of water at home, so you see the air bubble, and you have to keep it just for a few seconds so that all the bubbles are gone, and then you are going to drink it, right? So I mean to say that for any kind of purification treatment which you are going to apply in order to clean the contaminated water, you have to apply the treatment inside the aqueous bulk of the contaminated water. But this is not the case here. the treatment is simply applied from the air-water interface rather than putting the magnetic nanoparticle in the aqueous bulk. No filtration process is required to remove pollutants. Application of external magnetic field. So no filtration process is required, that you have seen. Application of external magnetic field can remove pollutants, loaded magnetic particles. Now, the uniqueness, why we have specifically used the magnetic nanoparticles, surface active magnetic nanoparticle, the reason is the removal of the magnetic nanoparticle from the interface is much easier. What if they are not magnetized? So then, what we have to do, we will need to perform the filtration or the centrifugation process. But in this case, you can simply avoid these complicated processes. Place the magnet, collect all, and remove the water, or clean water. So that is the advantage of the surface active nanoparticle. So this is all about the story which we have begun today for the surface active magnetic nanoparticle. We will continue with this. Hopefully you have understood. Thank you so much for your attention. And now you can ask me if you have any questions.
There will be a tea break.
Yeah.
And after the tea break,